Welcome back, everybody. In this video, we're going to look at cycloalkenes and briefly look at cycloalkynes. Just like cycloalkanes, cycloalkenes are rings of carbon atoms. The big difference, though, is that a cycloalkene has a double bond, at least one double bond, I should say, in the ring of carbons. So here I've shown a line structural formula for a 6-membered carbon ring, and there is a double bond between two carbons. If I were to draw a structural formula for this, it would look something like that. And we'll put in our hydrogens. So for the carbons that are part of the double bond, each carbon already has a double bond to the other carbon and a single bond to a second carbon. That gives us a bonding capacity of 1, and that is filled up with a bond to hydrogen. With the remaining carbons in our molecule, each one has a capacity for 2 more hydrogens. The result now is that we have a 6-membered carbon ring that has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 hydrogens. So this would be C6H10. And you can imagine if you were to draw rings, carbon rings of 4, 5, 6, and 7, maybe even 8, you could keep going. And if you have at least one double bond in the ring, the general formula for a cycloalkene, just that one double bond between carbons, will be CnH2n minus 2. So it's just like a normal alkene, except we take away another 2 hydrogens. That's a result of the carbons being in a ring. So as you can see, the general formula, CnH2n minus 2, this is also the same general formula for alkynes. So alkynes and cycloalkenes will have the same molecular formulas. So how do I name this thing now? Well, I have a 6-membered ring, 6-carbon ring, and there's one double bond. So the root is going to be how many carbons are in the ring. So there's 6, so that gives me a root of hex. There's one double bond, so that means the suffix has to be -ene, so hexene. And because it's a ring, I have to add the prefix cyclo. So this one's actually pretty straightforward. It's called cyclohexene. Now, because it's a ring, I don't need to indicate the position of the double bond. There are no branches or anything, so I don't need to number the carbons all that, because the double bond, by definition, in an unbranched cycloalkene will occur at carbons 1 and 2. It starts at carbon 1 and ends at carbon 2. So it doesn't really matter, it's going to always be 1 and 2. So I don't need to specify cyclohexene, because by definition cyclohexene will have its double bond starting always at carbon 1, no matter how you rotated this structure. Now it changes once you have a branch. So let's do an example like this. So imagine we have a cycloalkene that looks like this. If I were to name this, I would need to start numbering my carbons such that the double bond goes through carbons 1 and 2, and then any branches on the molecule get the lowest possible number. So first I'll show you the wrong way. So the wrong way would be to go this way. 1, 2, 3, 4, 5. So the wrong way would be going that direction, because then the branch gets the gets a higher number. The correct way, I'm going to do it in green, would to start carbon 1 here on the left, carbon 2 on the right, and then the branch gets the number 3, like that. So the correct way would go the other direction, which would be counterclockwise. So the correct name here comes from a 5-membered parent. So 5-carbon parent gives us the root of pent. The double bond always occurs at carbons 1 and 2, so it would be pentene. And since it's a ring, it's cyclopentene. And then we have a branch coming off the 3rd carbon. So the prefix would be 3-methyl, because it's a methyl branch coming off of carbon 3. 3-methyl cyclopentene. Okay, so the double bond always goes through carbons 1 and 2. And then you number the branches based on how you number the double bond. The branches need to be numbered so that they get the lowest possible number. So this gives us 3-methyl cyclopentene. If we went in the clockwise direction, we would get 5-methyl cyclopentene. So 3 is lower than 5, that's why we go with 3. All right, so that's naming and drawing cycloalkenes. Cycloalkynes are very similar. You could just imagine you've now got a triple bond in the ring. Other than that, I'm not going to spend really any time going over cycloalkynes. I don't think I've ever seen a cycloalkyne come up on a diploma. That being said, there probably is some example somewhere. But really, it's just the same thing. The triple bond would have to go through carbons 1 and 2. And instead of having a suffix of -ine, it would get a suffix of -ine. They're a little bit trickier to draw because in a triple bond, I don't know if you recall this, but you might recall that in a triple bond, it's a linear geometry for the carbons that are part of the triple bond, and that linear geometry extends up to the carbons that they're bonded to on either side. These ones would be, they could be tetrahedral, or they might even be trigonal planar. But these two carbons there would be linear. So it can be a little bit challenging, especially to draw a line structural formula for a cycloalkyne, because one part of that cycloalkyne has to have a set of 4 carbons that basically are perfectly linear. So the geometry can be kind of difficult to deal with when you're drawing, and your smallest cycloalkynes, I can't remember right now, but they're larger than you'd get for cycloalkenes and cycloalkanes because they have to accommodate this big piece right here. So that being said, I'm not going to spend much time drawing out cycloalkynes or going over examples of cycloalkynes. It's really just the same way of naming them, except you go -ine to -ine, and the triple bond goes through carbons 1 and 2. Same thing. All right, I'll see you in the next video. Next video is going to be about aromatic hydrocarbons. See you then. Bye.